have studied linear equations in two variables, then we study linear inequalities in two variables. Now we're going to discuss systems of this. So we're going to talk about systems of equations, and then we'll talk about systems of inequalities, and we'll stop there for the next exam. Okay? So let's go ahead and let's discuss system of equations. So we know how to solve one linear equation in two variables, which is just drawing the lines, right? That's the entire solution. Now what we want is we want to solve two equations simultaneously. If I give you two or more, then we want to solve that. So let's discuss how to do this. So I have some stuff already written down to save time. So we want to talk about system of equations, and basically a system of equations is when you have two or more equations, okay? You have two or more equations, and here you can see some examples. Like here you have one equation, and here you have another equation, okay? And typically we use these little curly braces just to say that we're solving a system. What does it mean to solve a system? So what's the meaning of a solution? I'm going to write it down right now. But basically what we're looking for is a point that's a solution to the first and the second equation at the same time. So you want something that solves both simultaneously, okay? So there are infinitely many points that work for the first one. There are infinitely many points that work for the second one. But which one works for both? That's what we're trying to look for, okay? That's what it means to solve a system. So here are two examples. Are there any questions on what a system of equation is? It's just when you have two or more equations, okay? And we use the curly braces saying, okay, look, I want to solve a system. I want to solve both of them simultaneously. So let me write that down. So what's a solution? So a solution to a system of equation is a point, okay? So it's going to be a point, x comma y, that is a solution to all equations in the system. I'm not saying two equations because it could be 3, 4, 20 equations, okay? We're only going to look at two, but it doesn't have to be two. You could have more than two. So that is a solution to all equations in the system. It's a point that's a solution to all equations in the system. All right. So let's see. Let's first try this. Here are some systems. Then I'm going to giving you some points. I want you to tell me if the points are solutions to the system or not. Okay. So if I already give you the point, how do you determine? Let's focus on number one, the first system, and the point -2, -4. How do you determine whether this is a solution to the system or not? Where? Into both equations. And what must happen for you to say yes? So you plug in, and then what? Yes. Then what you do? Just think about it. If you plug in, what do you do after you plug in? So let's see, what does it mean to be a solution? I mean, you want this to be a solution to both, right? So you plug in here because you want to see if it's a solution. So what is it that you have to look for? You want to see if you get a true statement. You want to see if the left equals the right. Yes? And then here the same thing. You plug in and you want to see if you get a true statement. You want to see if the left equals the right. If it works, then it's a solution. If one of them don't work, that's it. It's not a solution. Remember, we're looking for something that works with the first one and the second equation. What do we mean by works? When you put the x and the y, what you get here on the left equals what's on the right. That's all. Okay? All right. So by the way, if you put in the first one and it doesn't work, do you really need to check the second one? No, because you need it to work for both. If it doesn't work at the beginning, then that's it. You stop. Okay? Only if it works for the first one, then you move to the next one and check. Okay? All right, let's see. So for equation 1, for the first, we have 3. It's always good to put parentheses when you are plugging in. Okay? And then we're just wondering, is this equal to -8? So let's see. So x is -2, and then y is -4. It's always good to open parentheses where the variable is, and then you just put inside its value. So let's compute. So 3 times -2, that's -6. Then -8, right? Because 2 times -4. And then we're wondering, is this equal to -8? Well, -6 minus 8, that is -14. and this certainly is not the same as negative 8. Yes? So what does that mean? So it means this point is not a solution of the first equation, therefore it's not a solution of the system, because it doesn't work for the first one. So the answer is no, it's not a solution to the system. You understand this? Okay, so later we're gonna see, of course, you're not gonna be given a point, you're gonna be given the system, and your job is to find the point that works. But first, let's make sure that we understand what we're trying to find, okay? All right, let's see, do the next one. B, again, we're working for the first system. This is the solution. So let's see, do B, and then for the other two, and then the other 2 points are for the second system, okay? So do them, I'm gonna give you a couple of minutes. 3 minutes. Tell me which one works, which one doesn't. So B is only for the first one, and then these other two, this A and B, are for system number 2. Okay. So what do you get for B? Is it yes or no?
No.
No. Okay. Which one fails? The first one. Okay. Let's see. So let's plug into the first. So that would be 3. Gonna put my parentheses. Next 2, and then the question is this negative 8? All right. Let's see. 0, negative 6. So we're gonna get 0, so this is negative 12. Okay, negative 12 is not negative 8, so it's not a solution. We okay with this? No need to look at the second one. Good. Okay. How about the other one? No. All right. By the way, this you can quickly do it, right? Just by looking at it. When it's 0, plugging in 0 is very easy. So if you plug in x equals 0, you must get y equals negative 5 for the first one. So we have a 2, but it doesn't work. That's it. No, you don't even need to look at the second. Do you understand this? By the way, notice that this is a solution to the second one. Yes? If you put 0 here, then y is going to be negative 4 divided by negative 2, which is positive 2. So this point is on the second one, but it's not on the first one, so it's not a solution. Okay? So I'm going to plug in the first, which would be y plus 3x equals negative 5. You're wondering if this works or not. So that would be the 2 goes here and the 0 goes here. And then we have 2 equals negative 5. No, it's not good, so it's not a solution. Okay? All right. How about the other one?
Yes.
Does it work? Okay, so let's see. Let's do it visually. So x is negative 2, y is 1. If you put it in there, you're gonna get 1 minus 6, right? So that's negative 5. So that's a check for the first one. Then you put in the second one, you're gonna get negative 2. Then you put y equals 1, so it's minus 2. So negative 2 minus 2, that's negative 4. That's a check for the second one as well. So this guy is a solution. Okay? All right. So you just write it down here. So for the first, that would be so y. So just make sure that you put the correct numbers. So 1 minus 6 equals negative 5. Yes, that's good. And then for the second one, it was x minus 2y equals negative 4. So x, y. So as -2 minus 2 equals -4. Yes, that's good. So that's a big yes. So that's a solution. Any questions? So again, this is the kind of stuff that we're looking for. Okay. So given a system, we are looking for a point so that when you plug it into each equation, it works. It gives you a true state. Okay. Now, a natural question to ask is, well, okay, this is a solution. Could there be more than one? Are there more solutions? Okay, because we just found one. But are there two? Are there three? Are there infinitely many solutions? Okay, so let's discuss this. In other words, let's talk about how do we find solutions to a system. And the point is that there are three ways to do this. Okay, so the first approach is what we call the graphing method. So by graphing, this one is very nice conceptually, but it's not practical to actually do it. So we're gonna do just one example. You're gonna see how tedious it is. And the point is that you have to be very precise in your graph. So it's not really practical to do it. The other two are doing manipulations, algebraic manipulations. Those are the ones that we're going to focus on because those are the easier ones to find solution. They are more practical. So this is called the substitution method. So by substitution, and then there is another one that's called the addition method. So by addition. All right. So I'm going to explain the graphical approach first because this one will tell us some stuff about the system, which is you need to know. But then to actually find the solution, number one is not good. 2 and 3 are the way to go. Okay. So after today, we're just going to be using 2 and 3. But number one, we needed to get some information. Like for example, number one is going to tell us how many solutions we can expect. Okay. And actually, by understanding number one, you can tell if there will be a solution at all. Okay, so let's talk about that. So what we're gonna do now is discuss each of these. I don't think we're gonna have time for number 3, so we're gonna discuss number 1. If we have time, we do something about number 2, and then next time I continue with 2 and 3. Okay. All right. So the graphical approach. In other words, we're trying to understand how, given a system, we can come up with something like this. Okay, a point that works for both. Okay. So the graphing method. So let's see. Like the name suggests, if you want to solve a system by graphing, you need to graph something. Okay. Now, the first observation to see is that this system of equations, these are linear equations in 2 variables. Each equation is what? They are lines, right? So if you want to solve these 2 equations, you actually have 2 lines. And what you need to understand is that what we're looking for is a point that belongs to both lines. Because you want a solution that works for both, right? You want a point that belongs on the first line, but it also has to belong on the other line. That's what it means to be a solution. So every time that you have 2 lines that you want to study, there are 3 possibilities that could happen. What are they? Either the lines, they cross at a point, maybe they don't cross at all, so they are parallel, or they are one on top of each other, meaning they are the same line. Okay, and this can be seen easily. For example, you can think of the equation x plus y equals 3 and the equation 2x plus 2y equals 6. You may say, oh, those 2 equations are different, but no, they are the same equation. If you divide the second equation by 2, what do you get? The first equation. But if you multiply the first equation by 2, you get the second equation. So those 2 equations, those are 2 equations of the same line. So that would be a situation like this, in which you're seeing 2 equations, but you are really seeing the same line. Okay? All right? So to solve a system means that you want to find solution for both equations, the solution that works for both of them. Graphically, that means you want to find a point that lies on both lines at the same time. Okay? Now, these are the 3 possibilities. Can you think of another possibility that we could have graphically when you draw 2 lines? Either they cross or they don't. If they don't, it's this. If they cross, there are 2 possibilities. 1 point or all the points. I mean, there is no squiggly thing, otherwise it's not a line anymore. Do you understand this? A line cannot cross at 2 points. 2 lines cannot cross at 2 points. Okay? It's either 1 or all the points. So, and by the way, this guy right here is what we are after. This is our solution. Okay? So in situation number 1, what do we have? One solution. So here we have one solution. Do you understand this? If the lines close at a point, then that means that we only have one solution for the system. Situation number 2, the lines are parallel. What does that mean? So no solution. So the lines are parallel. So that means we're gonna have no solution. So it's possible to have a system in which we have no solutions if the lines are parallel. Okay. And then situation number 3, infinitely many solutions. Right? So these are the possibilities. You either have one solution, no solution, or infinitely many solutions. Okay? Now, can we tell which one is it by just looking at the equations? The answer is yes, because we know how to determine these things. We can look at the slope. For example, how do you know if you are in this case?
The same slope.
If the two equations have the same slope, then you know that the lines are parallel. Unless what? If they also have the same y-intercept, what does that mean?
They coincide.
Then they are the same line, same slope, same y-intercept, they're the same equation. Yes? So if they have the same slope but different y-intercept, you are here. No solution. Yes?
And that's after you solve it.
No, you can tell that before solving. That's the point. So it's good to know what's going to happen, because if there's no solution, why would you solve it? Right? So it's good to know what you're going to get beforehand. So if the slopes are the same but different y-intercept, meaning the lines are parallel, no solution. If the slope are the same and the y-intercept are the same, that means the lines are the same. So you are here, infinitely many solutions. So when will this happen? When will the lines cross at one point? If they have different slopes. If the slopes are different, you have only one solution. So that's pretty easy. So each of these cases, they have a name. Okay? So I'm going to summarize those cases now. So these are the type of system. So again, given two lines, these are the three possibilities. Okay? They cross at a point. So in other words, now we know that this means that there is one solution. There's one solution. What's the second case? This second picture, what does that represent? The no solution situation. And the last picture, what does it represent? Infinitely many solutions. Okay? So, and that's the situation. Now, how can we tell this? We can tell these cases by looking at the slopes. Okay? So, in the first situation, again, this is the solution right here. That point. And that's the one that we are after. So, in the first situation, what we can say for sure is that this happens because the slope of the first line is not the same as the slope of the second line. Yes? Different slopes, that's it. We have one solution. Now, the second situation, how can we detect this?
Same slope.
Same slope, but different y-intercepts. Yes? Because otherwise it would be the same line. So M1 equals M2, but B1 is different than B2. Yes? That's how you know that you are here in the no solution situation. And then in the infinitely many solution is because we have the same line. So M1 equals M2 and B1 equals B2. You know, you have exactly the same. So the equations may look different, but when you write them in a slope-intercept form, they will look the same because there is only one slope and only one y-intercept. Okay? All right, so that's how you can tell where you are by just looking at the slopes. Okay? And then, if necessary, the y-intercepts. Now, each of these cases have names. Okay? In the case that there is a solution, which is the first and the last, because here there is at least one solution, we say the system is consistent. And when there is no solution, which is here, we say the system is inconsistent. So the name that we use is, we say the system is consistent. System is consistent. And then in this case, we say the system is inconsistent. So the word consistent means there is at least one solution. Inconsistent means, okay, there's no solution. Now, how do we separate these two cases? Okay, there is something else which is called dependence. Okay, we say a system is independent if there is either one or no solution, and we say a system is dependent if there's more than one solution, like in this case, infinitely many. Okay, so we call this case system is independent. And same thing here. So this is how you classify the names that we use, okay? For example, if independent, if they tell you, oh, you have a system that's inconsistent and independent, you know that they're talking about a parallel situation. If they tell you the system is consistent and independent, we're talking about the first case, okay? One solution. And this one is consistent, dependent. The system is dependent. Okay, so that's the classification, the type of systems that we're going to have. So before you even solve, you can tell all of this by just looking at the equations. Okay, all you have to do is write in slope intercept form, look at it, and you will know exactly where you are. Okay, if you are here, then you don't have to do anything. You don't even need to solve. Just say, hey, there's no solution because slopes are equal and y-intercepts are different. So you stop. Okay, you would only do something if you are in this case. Because here you would just say there are infinitely many solutions, and then I'll show you how you write it down. And basically, it will be all points satisfying the equation. Okay, that's all you say. The only case that requires work is the first one. All right, any questions? Okay, so let's practice this. So here is the system, y plus 3x equals -5. This is the one that we found a solution before. Okay, so let us try to identify the type of this system before we even solve. Okay, so identify the type of system. So that means I want you to tell me whether it's consistent or inconsistent, and I want you to tell me whether it's dependent or independent. Okay, that's what this question means. All right, so for this, we need to know the slopes, right? So how do we know the slopes? What should be the first step?
Put it into y, put it in the slope intercept form.
To put them in slope intercept form. So that's the first thing that we should do. So the first thing that we should do is write it in slope intercept form. Okay, so let's see, the first one is easy, right? So what do I need to do for the first one? Just move the 3x to the other side. So that is y equals -3x minus 5. That's the first equation. Okay, now the second one, we need to do a little bit of work. Okay, so let me write it down here and let's do it. So we have x minus 2y equals -4. Let's see, who can tell me what's the slope intercept form of this? You did this for the first exam, so you should know this by now. Okay? So let's see, what's the first step? Who can tell me?
Subtract x.
Good. So we move the x to the other side. And now?
Divided by -2.
So we divide everything by -2. So, you know, every single term just divided by -2. So what do we get? Let's see, who can tell me? Y equals?
-x.
What's negative divided by negative? So what should I write? Which is, remember, we want to write mx plus b. So something times x plus something. So
1/2.
1/2. So 1/2 x. Remember, x over 2 is the same thing as this. Okay? It's the same. All right. And then?
+2.
Plus 2. Good. Does everybody understand this? Yes? So as the second equation, y equals 1/2 x plus 2. Okay, so this system is the same as the original one. Okay? It's just that now the equations here were written in slope intercept form because it's easier for us to analyze. Now let's look at it. What do we need to get from here to decide the type of system? What do we need? What do we need? Our job is to decide what column it is. What should you be looking at?
Slope.
Slopes. So tell me the slopes. What's the first slope?
-3.
First slope is -3. What's the second slope? 1 half. Okay, what can we say? Are they the same or they're different? They're different. So what's the conclusion?
System is consistent.
So M1 is different than M2. So think about the picture. How does the picture look like? The red line, is it going up or down?
Up, down.
It's going down, and the blue line going up. So you have a picture like that. So what do we have? One solution. Yes? So right here, you know that you are in this case. One solution. So how is the system? So the system is, if there is a solution, we say it's consistent. And then when there is only one, we say it's independent. So the system is consistent and independent. Again, you just need to learn this, okay? So use this as a little dictionary. If you are in this case, this is what you say. If you are in this case, you say this. The other case, you say just a little dictionary. Okay. Any questions? All right, so you did this. We look at it. Now we know there is a solution. Now, of course, okay, there's one solution. Great. Where is it? Okay. So now we need to know how to find this. By the way, we know what it is. We did it in the previous exercise, but I gave it to you, and you just checked and you saw that it works. Now let's find it. I'm going to explain to you how to do it via the graphing method. So what do you think the graphing method is? Let's see. Try to use common sense. What do you think we should do? When we say graphing method, what does that mean? What do we do? How do you find the point? You want to know this guy, so what do you think we do? You grab this line on the same x, y axis, you see the point, and then you read the x and the y. Now, you can imagine the problem with this, that you need to do an exact graph if you want to read the nice code, the good coordinates. And also, if the solution is -1,000,75, you're not going to see that in your picture, unless you have a huge paper to graph. So that's why I'm saying this is really not practical to find the solution. It's nice to understand the graphing approach because it allows, look, all of this we're able to say because we were thinking graphically. Okay? But to actually find the point, that's not good. We're just going to do one example, but then after that, we're going to learn the other ways, which is easier because it's just manipulating numbers. Okay? All right. So, let me say here, to solve the system graphically, what we do is we graph each equation on the same coordinate system, so the same xy axis, the same coordinate system. And then see where the graphs intersect or cross. Where the graphs intersect. So intersect means cross. Okay, where the graph cross, the point, or maybe points, because this is in general. This works for everything. For example, how many solutions can you have between a line and a circle? Imagine that your system is something that has a line and a circle. How many solutions do you think you're expecting? What would be the possibilities? Think graphically, the way that we just did. If instead of two lines, we're dealing with two lines, but what if you had a line and a circle?
And a circle?
Yeah. What would be the solutions? What are the possibilities? Your circle, you could have a line going this way, so no solution. You have your circle, you could have a line touching the circle at one point, so one solution, or you have your circle and you can have a line going through it. Two solutions. So if the system that you're dealing with has to do with a line and a circle, there are three possibilities, but the three possibilities are no solution, one solution, or two solutions. That's it. The infinity in many cases not possible. There's no way a line coincides with a circle all the time. So this is the graphical approach. Graphical approach says, okay, just draw the picture, the two pictures in the same place, and see if they cross or not. If they cross, the places where they cross, those are your solutions. Okay? If they don't cross, then there's no solution. That's basically what I'm writing here. Okay? And it doesn't have to be for lines. This applies for anything. Okay? Any equation. So to solve a system graphically, we graph each equation. Now the question is how do you do this? So far we only know how to graph lines. Okay? We haven't talked about circles. You will do that in college algebra. In college algebra, you will discuss circles. Okay? All right, so to solve a system graphically, we graph each equation on the same coordinate system and then see where the graph intersects. The point or points, could be more than one, where they cross is, or are, the solution. I'm writing here a general statement. That's why I'm putting the plural version as well. Okay, in parentheses. Okay, so example. Let's do the first one. Solve the above system. Again, the problem with this is that to be able to do it, to find this solution, you have to do an exact graph. If you're off in your scale by a little bit, that's it. You're not gonna see the coordinate. Okay, so that's why it's so painful and it's not practical. But it can have the advantage here of choosing graphing paper. So let's do it. Okay. Otherwise, it will be painful. All right, so let's do this. So the system is y plus 3x equals -5 and x minus 2y equals -4. Okay, so we already have the slope-intercept form of this guy, so the points are nice. So let me write them. So this system is equivalent to the following system. So the first equation was y equals -3x minus 5. That's what we got in the first equation. And the second equation was y equals, it was 1/2 plus 2, 1/2 x plus 2. Okay, those are the equations that we got here. Okay, I'm just rewriting these equations. All right, so why am I writing this? Well, because once you have a slope-intercept form, and because the y-intercept is a nice number, it's an integer, it's very easy to draw the lines. Okay, so otherwise you have to look for 2 points for each equation, plot them, and all of that business. Okay, so let's do it. I have my x and y. Okay, here I have to make sure that everything is straight. So cannot mess this up. That's my y-axis. And then, of course, you know, each little square represents a distance of 1, okay? X. All right, good. So let's draw the first line. So the y-intercept is -5. So that would be 1, 2, 3, 4, 5, right here. And then let's see, this line is going down, right? So the slope is -3, so that means there is a point down here. But I don't want to really go down here because I know the line goes like this. So I want to find the point that is up here. So let's practice that. Remember, if you want to find the point down, what do you need to do? Down and right. If I want to find the point over here, what should I do?
Up 3 to the left one.
So up and left. You know, just think about it. Okay. So that means that I should go up 3, but then 1 left. That's equivalent to going 3 down and 1 right. Do you understand this? Okay. All right. So up 3, 1, 2, 3. So that's -2, and then 1 left. So right here. Okay. And then I draw my line. It has to go exactly through the little squares. Otherwise, it's not gonna work. And I think I'm off here a little bit. It's just that my points are a little bit too thick. So, anyways, you should be able to tell from that. Okay, so let's go to the next one. So 1/2 x plus 2. So the y-intercept is 2. It's right here. And then this line goes up, so I should do 1 up, 2 to the right. So that's 3, and then 1, 2. That's the other point. And then we draw. Okay, so we have our first line, this is our first line, this is our second line, and then we can see clearly that they cross right here at this point. And then, you know, if we know this is the solution, this is the solution, and then all you have to do now is read it from the graph. You will only be able to read it successfully if we did a perfect graph, like the nice scale. Here, I kind of forced it here because we already knew what solution was, but the lines were a little bit off. Like if I, so that means that because the thickness of this thing is, you know, when you do the points, look, we're supposed to go through this nice intersection, okay? They went a little bit off just because this line is thick, and then probably here I'm not really going through. You know, there are many things that could happen that will lead you to get the wrong thing. So that's why this is not practical to actually find the solution. But if I do this, I kind of fix the problem. Okay? Anyways, the point is, this is the idea. You grab one line, you grab the other line, and then you can see a solution. It's right there. Now, can we read it from the graph? Well, in this case, and you know, should be able to tell. But if we do this, then this is a 1, and this one is a -2. So the solution is -2,1. Okay? But you know, this takes time, and even if you take all the time that you need, you might not even get it right because you could be off, and then you wasted a lot of time. So that's why we don't do this to solve a system. But it has some advantages, as I mentioned. It allows to conceptually understand what we're doing. You know that when you solve a system, you're looking for 2 lines crossing each other, and you want to know when they cross. That's what you do. All right. So anyways, looking at this, we can see the solution is, so the solution is a set, but this set is only has one element, is a point, -2,1. So a solution to a system is a point, okay? So that's what you write, the point -2,1. Which of course, this was the one that we verified earlier. Here, -2,1. Okay, questions? Did you understand how we found this point graphically? Okay, so in the homework you will have a couple of problems like this, but the homework is nicer because you just click and stuff. So when you do it, it will be the exact thing. So just make sure that you can read off, okay? But in paper, it's really painful. So let me show you. I'm gonna redo the same problem by using, to illustrate to you, the substitution method, so you see how it works. Then next time, just gonna do more examples. Okay? Any questions? All right. So hopefully you realize that this is not practical. So to actually find this point, we need to do something else. So let me show you the substitution method. It should be pretty straightforward. So I'm gonna illustrate this via an example. So example, solve the system. And then later, you know, I'll tell you the steps and all that business next time. I will just say the steps now, but I will not write them formally. You just see me doing the problem. Okay, so typically we like, when we are going to work, so we can justify our work and follow what's going on, we like to number the equations. So the first one I'm going to call it equation number 1, the second one I'm going to call it equation number 2. So here is the idea. Like the name suggests, substitution. So the point is that if this has a solution, it means that there is an x and a y that works for both equations at the same time. So this x is the same as this x down here, this y is the same as this y down here, okay? So what's the idea? Okay, take one equation, solve for one of the variables, and then that expression, you substitute it or you plug it into the other equation. By doing that, you get rid of one variable, and then you will have a linear equation. You solve it, and then you're pretty much done. That's the idea. So let's say in this case, it's pretty easy to choose either one. So let's see, which one do you want to solve for, x or y? Tell me a variable that you want to eliminate, x or y?
I'll get rid of it. I'll just say y.
Which one, x?
Sure.
Okay, so we can get rid of x, but now we should use second equation because it's easier. Just have to move this guy over, okay? If you use the first equation to solve for x, you have to divide by 3. That will be a pain. You have fractions, okay? So here, I'm going to use equation 2 to solve for x. If you wanted to eliminate y, you could use equation 1 and just move the 3x over and you eliminate your y, okay? But anyways, let's just eliminate x. So I'm going to use number 2 to solve for x. So number 2 tells me that x is minus 2y equals -4. So that means that x equals 2y minus 4. Does everybody understand this? So remember, this x is the same in the top. So now what you do is, this expression, you plug it into the first one. So now, what we're going to do is, we're going to plug x equals 2y minus 4 into equation number 1. Okay? So that would look like 3. Now, instead of x, you put what it is, which is 2y minus 4, right? Equation 1 says 3 times x plus y equals -5. Okay, I know that x equals this because the second equation, you put it there. Now what do we have here? A linear equation in one variable, so we know how to solve this, so let's solve it. So now we solve for y. So this is 6y minus 12 plus y equals -5. Move the 12 over and combine like terms. So we get 7y equals -5 plus 12. What's -5 plus 12? Positive 7.
Oh, yeah, sorry.
So what is y? 1. And now once you find your y, remember we need to know x. How do we find x? Well, we know that x equals 2y minus 4. Put it here, and it tells you your x. So x equals 2y minus 4, but now we know that y is 1. So that's 2 times 1 minus 4. So x is 2 minus 4, which is -2. And that's our point. So the solution is, remember, it's x comma y, -2 comma 1. So this is what's called the substitution method. Should be clear why. The idea is just use one of the equations to solve for one of the variables, whichever you choose, whichever you think is easier. Then whatever expression you get, you plug it into the other equation, and you will get a linear equation in one variable. Solve it, and then that value you use it to recover the other value. You're done. You okay with this? All right. So next time I'm gonna keep on this and show you the other way.